Hello, my chemistry friends, and welcome to our next lesson in Unit 7. Today we are on Lesson 7.2, where we will be talking about what are called potential energy diagrams. Our two main learning targets for today, we want to be able to use potential energy diagrams to identify reactions as either endothermic or exothermic, and we want to be able to identify the 6 main values from any potential energy diagram. These will make sense as we go through our lesson. Today, your to-do list, hopefully you have already finished your warm-up. Right now, you should be completing your Edpuzzle or doing the live lesson. After this, you will have a classwork assignment where you're going to be practicing mastering our learning targets for today, and then you'll end with an exit ticket as always. Just to very briefly go over your warm-up for today, your first questions were asking you about entropy. As a reminder, entropy is a measure of randomness, chaos, and disorder. What we have talked about with entropy in the past is going to be differences in entropy with phases of matter. Gas particles are the ones moving around the most with the least organization, and so that is going to be a high level of entropy. And then solids, where yes, they are moving, but they're moving in a more organized pattern, you can predict their locations, is going to be our low entropy. Okay, that will be important later on in this unit, so I wanted to review it. And lastly, we reviewed what we learned in our last class, which is the main points of collision theory, which is in order for a chemical reaction to occur, particles, number one, must collide, and to be an effective collision, they must collide with enough energy and in the proper orientation or position. The more effective collisions you have, the faster your reaction will happen. So talking about that, we're going to be learning about what are called potential energy diagrams today. You can read what's on the slide, or you can look at this diagram. Basically, it's these like roller coaster looking graphs here, and our objective today is to, number one, learn what these are, be able to look at these to see if what we're dealing with is an endothermic or exothermic reaction, and then identifying the 6 main points on these graphs. You may be able to look at this and identify 3 of them, but there are 6 ones that we're going to learn today. To give you an introduction, I'm going to turn over to a YouTube channel called Science Dave, and he's going to give you the basics of potential energy diagrams.
We learned a lot about chemical reactions, but what is necessary for a reaction to occur on the molecular level? Collision theory states that molecules involved in a reaction, whether in the liquid or gas phase, have to collide in a particular orientation and with an amount of kinetic energy that exceeds the activation energy of a reaction. This is the amount of energy that has to be provided to allow for the reaction to proceed. Here we can see that the 2 molecules have to collide in a particular way in order to react. Otherwise, they will bounce right off each other. As for energy, let's refer to an energy diagram. On these, up means higher energy, and to the right means later in time. So we can see that any reaction will have an activation energy, which is the kinetic energy that the molecules must collide with in order to reach the transition state. This is the orientation which, once reached, the reaction will certainly occur. Collisions with less energy than this will not result in a reaction. From energy diagrams, we can also see delta H, or the difference in energy between the reactants and products. If the products sit lower, it is an exothermic reaction which releases energy. If the products sit higher, it is an endothermic reaction and needs to absorb energy to occur.
Alright, so he went through the basics. He went through them pretty quickly, but we're going to go through each one in detail. I have the skip feature turned off, meaning if you got what you needed to get from that video, you can skip through and answer the questions, but if you're hesitant at all, please go back and watch my portion of the video for a deeper explanation. So we are going to start off with our potential energy diagrams at the beginning of a reaction, and the stuff you have at the beginning is called the reactants. On our graph, that's going to be A plus B right here. This value is going to be known as the heat of reactants, or the amount of potential energy stored in the reactants. The symbol that is used to represent this, as shown in the video, is a capital H representing thermal energy, and then a capital R in the subscript position. So for this graph, the heat of reactants is going to be 40 kilojoules. It's going to be the distance from here up to the top. Next is going to be the heat of products, which hopefully you have guessed is going to be the amount of energy stored in the products. The symbol for which is going to be capital H with a capital P in the subscript position. And on our graph, that's going to be 20 kilojoules here, which is the difference from 0 up to this ending point right here. Those are the two main critical points that you will see on your graph, and we're going to focus just on those two now. We'll talk about this guy up here in a second. So the next one that I'm going to go through is extremely important. It's the one the Regents will always ask you about, multiple choice, short answer, whatever, it's always going to come up. And it's going to be the difference between your starting and ending point. And that is going to be known as the heat of reaction, the net amount of thermal energy that is lost or gained through a chemical reaction. Our symbol for this is going to be delta H, and it is the change in heat from the beginning to the end of the reaction. So on your graph, that's going to be the in-between of your starting and ending point. Okay, and what I'm about to show you next is extremely important. When you are doing potential energy diagrams, comparing the end to the beginning in terms of energy is extremely important. So when we're calculating delta H, or the heat of reaction, it is extremely important that it's always the heat of products minus the heat of reactants. The order is extremely important here. So important that this is often a multiple choice question. Delta H is defined as blah, blah, blah. Okay, and so it's important to remember that you're always going to do the end minus the beginning. Okay, so let's go through an example with this graph. So we want to find delta H, and we just learned that delta H is equal to the heat of products minus the heat of reactants. So what we already know is the heat of reactants is 40 kilojoules. It's going to be from 0 up to this point here. And we already know the heat of products, which is 20 kilojoules. Now to find delta H, you are always going to do heat of products minus heat of reactants, which hopefully you put 20 minus 40. And so our final delta H value is negative 20 kilojoules per mole. Okay, the negative is important. We'll talk about it here in a second, but our final units will be kilojoules per mole. So if I need to make 1 mole of C and D, I'm going to need negative 20 kilojoules of energy overall. Okay, so now why is that negative important? We have learned previously these two vocabulary words, endothermic versus exothermic. They represent the two types of energy exchanges that can happen. So when we're starting with reactions that release energy, known as an exothermic process, we are going to see delta H being negative, meaning we're ending with less energy compared to what we started with. In a chemical reaction, negative delta H, or an exothermic process, will have energy located in the product side, meaning you released that energy as a result of your reaction. An example, when we put the group 1 metals such as sodium in water, you release heat and fire, and it exits the system because it is an exothermic process. You are expected to be able to look at a potential energy diagram and either mathematically or just visually identify it as endothermic or exothermic. A quick way to do this is to compare the reactants and the products. This graph is showing you an exothermic potential energy diagram, and as you can see, the products is going to be less than the energy stored in your reactants. That will always be the case. If you end lower than where you started, you will know you have an exothermic process. The opposite of an exothermic process is a reaction in which the energy is absorbed, and we call that an endothermic system. In a chemical reaction, you will see the energy as a reactant because delta H will be positive. Okay, and when delta H is positive, you'll put it here at the beginning. An example, anytime you're cooking or baking or anything like that, you need to add energy to make it happen. Energy has to enter the system. So hopefully you guessed that an endothermic process will look the opposite, in which your reactants are lower than your products, meaning the net energy is positive. You have to add energy to make it happen. This is why it is important that you always do products minus reactants, because that will give you either a positive or negative delta H. We'll be looking closer at delta H in our next lesson, looking at table I in your reference table. If you want to get a head start, you can look at that and see if you can figure out what some of it is saying. So I'm going to give you a few practice problems. You're going to get 2 questions per graph. These are not graded. These are just practice. I want you to tell me whether or not the graph you are seeing is endothermic or exothermic, and then actually calculate the delta H value. All right, so hopefully you did pretty well on those questions. If not, please go back and review the video portions and see if you can correct your answers as you go. As a reminder, those are not graded, they're just check-ins, so if you answered them, you get full credit. The questions at the end, however, will be graded. So now what we're going to talk about is the curve on the top of the potential energy diagrams. We know about the beginning, the end, and the in-between, but now we're going to talk about that top portion. And this is representing something called activation energy, or the energy needed to activate or start a chemical reaction.
Right now, trillions of chemical reactions are humming away in the cells of your body. You never feel them, but without these reactions, you wouldn't be alive. Unfortunately, each of those reactions needs some help. You see, most molecules are stable. They're happy just the way they are. The atoms in them are all bound up and friendly with one another, and would prefer to stay that way. Problem is, for a chemical reaction to happen, the atoms that make up those stable molecules need to break away from their friends and go buddy up with another atom. This breakup is where the molecules need a hand. This initial kickstart is known as activation energy. It's used to destabilize the molecule, to push the bonds between the atoms to a place where they are ready to break. This unstable state is known as the molecule's transition state. Once the transition state has been achieved, the atoms become willing to leave their current molecular friends and go make new friends elsewhere. Once they're convinced, it's a piece of cake. Bonds break, atoms rearrange, and the rest of the reaction happens automatically. After that first push, the body doesn't need to put in any more energy to help the reaction along. Left alone, most of these reactions would be very slow, because it takes quite a while to build up the activation energy the molecules need to get started. Enter the enzyme. Enzymes are proteins that speed up or catalyze reactions.
Alright, so we'll talk about enzymes and things in our next lesson, but let's focus on that activation energy and how we can see it on these potential energy diagrams. So far this is what we've learned. We know that the beginning is called our heat of reactants, our end is called the heat of products, and the difference between two is our delta H, or heat of reaction. Now we're going to talk about this hill up here at the top. So this is what is going to be called the activated complex, or the transition site. Ultimately, by itself, it doesn't really matter, but what we want to look at is how much energy we need to get from where we're starting up here to this top part. And this is what is going to be known as the forward activation energy. And to calculate it, basically you're going to do the difference. We know we're starting at 40, and for this graph we want to get all the way up to 100. So for us, our forward activation energy is going to be the difference, 100 minus 40, to give us 60 kilojoules of energy. Okay, when we are doing activation energies, they will always be positive, so you can always do this top number minus your starting point. Now next week we're also going to learn about what are called reversible reactions, and so we also want to look at what's called the reverse activation energy, meaning we're going backwards. And so for this one, it's essentially the same thing. We need to figure out how much energy we need to get from where we're starting, but this time we're starting at our products, and go all the way up to that activated complex. This is going to be known as our reverse activation energy, and it's going to be your highest point minus your starting point. So for us, that would be 100 minus 20 to give us 80 kilojoules of energy. Okay, so you have learned the 6 main points on a potential energy diagram. You might be asked to find the heat of reactants, the forward activation energy, delta H, the heat of products, or the reverse activation energy. You very seldomly will be asked to identify the activated complex energy, but you need it to calculate both of these activation energies. Okay, So what we're going to do very quickly is I'm going to give you a couple of check-in questions, and they're all going to have to do with this graph here. But if you want to, I recommend taking a picture of this, writing it down in your notes so that you have it. But these are going to be the main things that you need to do with potential energy diagrams. All right, so you've finished your second part of today's lesson. Next, you have some classwork and then an exit ticket. If you have any questions, please reach out. But otherwise, thank you and have a great day.